I think we can do better than just timing. And my proposal for how we're going to do better is we can count the number of operations there are when our function gets executed. Counting operations. How do we count operations? Well, let's assume that all of the most basic operations, all the operators that we've learned, take a constant amount of time. Let's just say they each take 1 second. Well, actually, you've seen the program runs really quickly, so actually maybe it takes 3 nanoseconds to do an addition or to do each operation. Let's just say 1 unit of time, whatever unit that is. So all these mathematical operations that we've learned, all the comparisons, all the other kinds of operations like assignments or indexing into a list. And then let's look at the code and count the number of operations executed as a function of the input size. And you'll see in a second what that means. But let's take a look at this example. So that Celsius to Fahrenheit example that we were looking at before. So our input, the size of our input, C could be a small number or a big number, 0 degrees Celsius or 100 degrees or 1,000 degrees. I point out here as a function of our input size. Well, actually, it doesn't matter how big our number is. We still do the same number of operations here. So what are those operations? One is we have to get the value of C, so referencing C, and then we multiply by 9, we divide by 5, and we add 4. So there are 4 operations that happen here. Let's take a look at another example. So this function, def my sum x, total equals 0, for I in range x plus 1, total equals total plus I. So what does this function do? Take a second and see if you can figure it out. This function adds up the numbers from 1 up to and including x. And so this is a good example where because our for loop depends on this x, so the bigger x is, the more times this body will be repeated. This is where this function of input size comes in handy. The larger our input is, the longer our program will take to run because we have to add more numbers together. So let's think about what our how many operations here we have. So setting total equal to 0, that's one operation. That's an assignment. Now, then we have a range. So this for loop with this range means we're going to loop x times. So we're going to repeat the body here x times. And now in our body, yes, so one more thing before we talk about the body is that we loop x times, and notice that each time we need to increment, that is one operation, right? So the very first thing we do is we get the next number in our list, which really just sets I equal to something, and so that's an assignment that takes one operation. And then inside the for loop, total plus I, this is an addition that takes one operation. Storing the total, so assigning the result is one operation. And finally, so that's we finished the inside of the body. Finally, returning the total is one operation. And so let's write this out as a function of input size. What is the total runtime of my function? The total number of operations, to be very precise. So total number of operations is 1, because we always set the total equals 0, plus 3 times x, because the loop repeats x times. And we do inside here, every time we increment by 1, and then we add together 2 numbers, and then we store it into total. And actually, to be super precise here, this should be just up to x. Whoops. So we'll continue here. Yeah. Just up to x, so that it actually happens x times, right? Looping x times, because we start from 0. So when we do range x, that generates x numbers starting from 0 going up to x minus 1. And so inside 3x, that's the number of operations that happen in here. Assigning a number to the next number in the sequence to I, adding total plus I, and then assigning that result to total. And finally, returning is one operation. And so the total number of operations when you run this function is 1 plus 3x plus 1, so 3x plus 2 total, given a certain x as input. Now, let's look at something interesting here. Notice that my sum, the same function we just looked at, the same algorithm can be implemented a couple different ways. You can implement it with a for loop or a while loop, but the approach is exactly the same. Count up from 0 to x, non-inclusive, in either one. And we've just seen how many operations it is on the left, but I want you to take a minute and see if you can count how many operations it is for this implementation with a while loop. Same exact algorithm, just implemented with a while loop instead of a for loop. Take a minute to do that, and then I'll show you the answer. Okay. Hopefully you've done that, and let's see if you got what I got. So total equals 0 is one operation, I equals 0 is one operation. And inside this while loop, because we're looping until x, we're going to loop x times. But notice, for each iteration of the loop, we have to do one comparison here. So I compared to x. And inside the while loop, we have to do total equals total plus I, which is two operations, and I equals I plus 1, which is two operations. And finally, returning is one operation. So when we add these up, we get 1 plus 1 plus x times, we do 1, 2, 3, 4, 5 operations plus 1. And so that's kind of interesting. Like the same algorithm implemented two different ways gives us 5x plus 3 operations versus 3x plus 2 operations. We'll come back to that in a minute, why that's interesting. One more example I want to show you is a nested loop. And so we talked about this in class at one point a little bit, but given kind of x here, take a second. How many times do we print I comma j onto the screen in terms of x? So this outer loop happens x times, and then each time the outer loop happens, the inner loop runs and prints x times as well. And so x times, we print x times, so we get x times x, or x squared times. So for some given x, this happens x squared times, x squared operations. Okay, so this seems better. This will vary between different algorithms. And that's a promising sign. But a couple other things we need to sort out before we can be kind of okay with where we're at. One thing is, it's kind of interesting, the same list or the same length of the list, the same size of the list can change how the program runs. So for example, this search for an element function. Notice how for item and list, if item equals element, we return true. So we return true as soon as we find an element that matches. So imagine we're looking through the list 1, 2, 3, 4, 5, and we're looking for the element 1. What would happen? So element that we're looking for is the first in the list. Well, immediately, all we would do is one assignment, item equals list 0, and then one comparison, and it would be true, and so we'd return true. And so that would take only 2 operations. Whereas what if the element just isn't in the list at all? Then we have to do one assignment per element in the list, and then one comparison per element in the list. And so for a list with n items, we have to do 2n operations. In fact, maybe plus 1 for this return. So 2n plus 1 operations in the worst case. Or like if it's at random, probably on average we have to look through half of the elements in the list. So 1/2 n. And we want to measure behavior in a general way that kind of, we don't have to specify, what exactly the ordering of our list is. We just want to think about the size of our list. And as things get bigger, what do they do? And so this is where you want to think about best case, average case, worst case. So in terms of the length of the list, our best case is constant because it takes just one operation to figure out that we found the item in the list. And in the average, it takes about half the length of the list. And as we just said, in the worst case, you have to look over the entire length of the list. And so it's linear. It takes 2n operations. And just to have some consistent way of thinking about things, we're going to say that we always care about the worst case behavior. So what if you give us just the worst possible input what will happen. Okay, so now we have a way of talking about things. We have a way to say, okay, we're going to count the number of operations in the worst case possible input. But we still have this weird thing that you saw, that the number of operations actually varies between implementations, even for the same algorithm. It's nice that this doesn't depend on which computer is being run. So is it a weaker computer or a stronger computer? But it's kind of strange. You might have noticed, hey, why didn't we count range as a function, right? So how many units of work does it take to make a range? We didn't count that. It's unclear what exactly we should count as an operation. But it is nice that we can think in terms of the input size. And so we can say, this is the number of operations for an input of size blah. Maybe it's the length of a list, or the length of a string, or just an integer as input. But we do still need a better way, because timing can evaluate machines. That's not great. Timing and counting is better, but it still evaluates implementations. But we wanted to evaluate algorithms and how they scale and how they change in terms of input size. And the way we're going to do that will come in the next lecture as we talk about big O notation. I'll see you there. Bye.